Polynomials. In class 9, we have learnt the definition of a polynomial in one variable, its coefficients, its terms, and the leading term. We have also learnt about the values and the zeros of a polynomial. Here, in this chapter, we will discuss some relationships between the zeros and the coefficients of a polynomial. Some simple problems on division algorithm will also be discussed. We will start with a brief review of some concepts which we have already learnt in the previous class. Polynomials with real coefficients. For a non-negative integer n, an algebraic expression of the type shown forms a polynomial of degree n in variable x. The expressions a0 x to the power of n, a1 x to the power of n minus 1, an minus 1 x, and an are called the terms of the polynomial. Here, a0 x to the power of n is the leading term of the polynomial. The numbers a0, a1 up to an minus 1 and an are all real, and they are called the coefficients of the terms of the polynomial. The same polynomial can be written in some other variable, y or u or t, etc. as below. A polynomial in variable x can be denoted by the symbols like f of x, g of x, h of x, p of x, q of x, etc. Similarly, a polynomial in variable y is denoted as f of y, g of y, etc. Thus, we can write f of y, f of u, and f of t as shown below. Polynomials with real coefficients. Let us write a few polynomials in single variable with real coefficients. 2x plus root 3 is a polynomial in the variable x of degree 1. 7y plus 5, root 3y minus 4, 13y minus 5, 7 minus 11y are polynomials in the variable y of degree 1. 3x squared minus 5x plus 1 is a polynomial in variable x of degree 2. Root 2u squared plus 7 is a polynomial in variable u of degree 2. It can be expressed as root 2 u squared plus 0 u plus 7. Minus 3 y cubed plus 4y squared is a polynomial in variable y of degree 3. It can be expressed as minus 3y cubed plus 4y squared plus 0y plus 0. 2x to the power of 7 minus 13x to the power of 6 plus root 2x is a polynomial in variable x degree 7. Expressions like x to the power of minus 2 plus 2x to the power of minus 1 plus 3, root x plus 3, etc. are not polynomials. Linear polynomial. A polynomial of degree 1 is called a linear polynomial. We write some linear polynomials with real coefficients and in single variable as under. We express a linear polynomial in general form as ax plus b in variable x, ay plus b in variable y, and au plus b in variable u. Here, a and b are real coefficients, a not equal to 0. Throughout in this chapter, we will discuss polynomials with real coefficients. Quadratic polynomials. A polynomial of degree 2 is called a quadratic polynomial. For example, 2y squared minus root 3y plus 7 is a quadratic polynomial in variable y. Ax squared plus bx plus c is a quadratic polynomial in variable x, is standard form where a, b, c are real coefficients and a not equal to 0. Cubic polynomial. A polynomial of degree 3 is called a cubic polynomial. Standard form of a cubic polynomial in variable x is ax cubed plus bx squared plus cx plus d. For example, 2x cubed minus 3x plus 6 is a cubic polynomial in variable x, and in standard form it is written as 2x cubed plus 0x squared minus 3x plus 6. Polynomial of degree n is standard form. a0x to the power of n plus a1x to the power of n minus 1 plus up to plus a n minus 1 x plus a n, a0 not equal to 0, and n being any whole number is a polynomial of degree n in standard form. A polynomial is expressed in standard form if the powers of variables in the terms of the polynomial are in decreasing order. For example, standard form of the polynomial 2x squared minus 3 plus 4x cubed minus 3x to the power of 4 is minus 3x to the power of 4 plus 4x cubed plus 2x squared minus 3. Values of a polynomial. Let us consider polynomial p of x is equal to x cubed minus 2x squared minus 2x minus 3. If we replace x by 1 in the above polynomial, we get p of 1 is equal to 1 minus 2 minus 2 minus 3 is equal to minus 6. Thus, p of 1 is equal to minus 6 is the value of the polynomial p of x at x is equal to 1. If k be any real constant and we replace x by k in the expression of p of x, then the value so obtained is called the value of p of x at x is equal to k or at k, and is denoted by p of k. Zeros of a polynomial. Real constant k is a zero of a polynomial p of x if p of k is equal to 0. For example, polynomial p of x is equal to x squared minus 7x plus 10 gives p of 2 is equal to 4 minus 14 plus 10 is equal to 0. And similarly, p of 5 is equal to 0. Thus, 2 and 5 zeros of the polynomial p of x is equal to x squared minus 7x plus 10. In the previous class, you have learned to find the zeros of linear polynomials. A linear polynomial has one and only one zero. Let us find the zero of a linear polynomial 2x minus root 3. Put 2x minus root 3 is equal to 0 and solve this equation for x. We get 2x is equal to root 3. That is, x is equal to root 3 by 2. Now, we find the value of polynomial. P of x is equal to 2x minus root 3 at root 3 by 2. In general, if p of x is equal to ax plus b, then p of k is equal to ak plus b is equal to 0. K is equal to minus b by a. So, 0 is linear polynomial. Geometrical meaning of the zeros of a polynomial. We know that a real number k is a zero of polynomial p of x if p of k is equal to 0. But why are the zeros of a polynomial so important? To answer this, first we will see the geometrical representation of lines and quadratic polynomials and the geometrical meaning of their zeros. Consider the first linear polynomial ax plus b is equal to 0, a not equal to 0. You have studied in class 9 the equation of straight line is y is equal to mn plus c. Y is equal to 2x minus 5. Solution intersects the x-axis midway between x is equal to 2 and 3, that is, at the point 2 and 1 by 2, 0. You also know that the 0 of 2x plus 3 is minus 3 by 2. Thus, 0 of polynomial 2x plus 3 is the x-coordinate of the point. Where the graph of y is equal to 2x minus 5 intersects the x-axis. In general, for a linear polynomial ax plus b is equal to 0, a not equal to 0, the graph of y is equal to ax plus b, straight line which intersects the axis at exactly one point, namely minus b by a, 0. Now, let us look for the geometrical meaning of 0 of a quadratic polynomial. Consider the quadratic polynomial x squared minus 3x minus 4. Solution: mark the scales on the graph sheet on x-axis 1 cm is equal to 1 unit and y-axis 1 cm is equal to 2 units. Assigning values of x is equal to minus 4 to 4, we calculate the values for y and prepare the following tables.
Represent the zeros of a quadratic polynomial minus x square plus x plus 6 graphically. Solution: we will draw a graph of an equation y is equal to minus x square plus x plus 6 as shown. Represent the zeros of a polynomial x cube minus 4x graphically. Solution: the graph of the equation y is equal to x cube minus 4n meets the x-axis in the 3 points a minus 2, 0, o 0, 0 and b 2, 0. Hence, minus 2, 0, 2 are the zeros of the polynomial x cube minus 4x and these are the points a and o.
Relationship between the zeros and the coefficients of the polynomial. Let us start with a linear polynomial p of x is equal to 2x plus 5. 2x plus 5 is equal to 0. 2x is equal to minus 5 gives x is equal to minus 5 by 2. That is, minus 5 by 2 is 1 and only one zero of the polynomial. P of x is equal to 2x plus 5. We observe that the zero of polynomial 2x plus 5 is equal to 5 by 2 is equal to minus constant term by coefficient of x. Thus, 0 of linear polynomial is equal to minus constant term by coefficient of x.
Find the zero of the quadratic polynomial. Verify the relation between zeros and coefficient of polynomial. Solution: px is equal to 2x square minus 8x plus 6 is equal to 2x square minus 6x minus 2x plus 6 is equal to 2x into x minus 3 minus 2 into x minus 3. X minus 3 into 2x minus 2 is equal to x minus 3 into x minus 2 into 2. Now, the value of px is equal to 2x square minus 8x plus 6 is 0 when x minus 3 is equal to 0 or x minus 1 is equal to 0 implies x is equal to 3 and 1, that is 1 and 3 are the two zeros of the polynomial px is equal to 2x square minus 8x plus 6. Sum of the zeros is equal to 1 plus 3 plus 4 is equal to minus of minus 8 by 2 is equal to 8 by 2 is equal to 4. Product of the zeros is equal to 1 into 3 is equal to 6 by 2 is equal to constant by coefficient of x square. Find the zeros of a quadratic polynomial 5x square plus 14x minus 3 and verify the relation between the zeros and coefficient of the polynomial. Solution: Px is equal to 5x square plus 14x minus 3 is equal to 5x square plus 15x minus x minus 3 is equal to 5x into x plus 3 minus 1 into x plus 3 is equal to x plus 3 5x minus 1. F of x is equal to 0. X plus 3 is equal to 0 or 5x minus 1 is equal to 0. X is equal to minus 3 or 5x is equal to 1 implies x is equal to 1 by 5. Then minus 3 and 1 by 5 are the two zeros of the polynomial 5x square plus 14x minus 3. Sum of the zeros is equal to minus 3 plus 1 by 5 is equal to minus 15 plus 1 by 5 is equal to minus 14 by 5 is equal to minus coefficient of x by coefficient of x square. Product of the zeros is equal to minus 3 into 1 by 5 is equal to minus 3 by 5 is equal to constant term by coefficient of x square. Thus, conclusion is the same for each quadratic polynomial. Find a quadratic polynomial, the sum and the product of whose zeros are 2 and minus 3 by 5 respectively. Solution: let the required quadratic polynomial be ax square plus bx plus c. A is not equal to 0. If zeros have sum is equal to 2 is equal to minus b by a, equation 1, and product is equal to minus 3 by 5 is equal to c by a, equation 2. Now we select a is equal to 1, 5 is equal to 5. Then from 1 and 2 we get b by 5 is equal to minus 2 implies b is equal to minus 10. C by 5 is equal to minus 3 by 5 implies c is equal to minus 3. Thus substitute a is equal to 5, b is equal to minus 10 and c is equal to minus 3 in ax square plus bx plus c. We get the quadratic polynomial px is equal to 5x square minus 10x minus 3. Find a cubic polynomial with the sum. Sum of products of its zeros taken 2 at a time. The product of its zeros are 4, 1, minus 6 respectively. Solution: let ax cube plus bx square plus cx plus d be cubic polynomial having roots alpha, beta, gamma. We given that alpha, beta, gamma is equal to 4. Alpha, beta plus beta, gamma plus gamma alpha is equal to 1. Alpha, beta, gamma is equal to minus 6. Minus b by a is equal to 4. 1. C by a is equal to 1. 2. And minus d by a is equal to minus 6. We select a is equal to 1, 1, 1 is equal to 1. From 1 we get b by 1 is equal to minus 4 by 1. That is b is equal to minus 4. From 2 we get c by 1 is equal to 1 by 1 is equal to c is equal to 1. From 3 we get d by 1 is equal to 6 by 1 is equal to d is equal to 6. P of x is equal to x cube minus 4x square plus x plus 6. In general, if alpha, beta are zeros of quadratic polynomial, px is equal to ax cube minus bx square plus c. A is not equal to 0. Then you know that x minus alpha and x minus beta are the factors of px. Therefore, ax square plus bx plus c is equal to k into x minus alpha, x minus beta, where k is a constant, is equal to k into x square minus alpha plus beta into alpha beta is equal to kx square minus k into alpha plus beta x plus k alpha beta. Comparing the coefficient of x square, x and the constant terms on both sides, we get a is equal to k, b is equal to minus k alpha plus beta, and c is equal to k alpha beta. This gives alpha plus beta is equal to minus b by a, alpha beta is equal to c by a, that is sum of zeros alpha plus beta is equal to minus b by a is equal to minus coefficient of x by coefficient of x square. Product of zeros is equal to alpha beta is equal to c by a is equal to constant by coefficient of. Find the zero of the polynomial x square minus 3 and verify the relation between the zeros and the coefficients. Solution. Recall the identity a square minus b square is equal to a plus b into a minus b. Using it, we can write x square minus 3 is equal to x plus root 3 into x minus root 3. So, value of x square minus 3 is 0 when x is equal to root 3 and x is equal to minus root 3. Sum of zeros is equal to root 3 minus root 3 is equal to 0 is equal to minus coefficient of x by coefficient of x square. Product of zeros is equal to root 3 into minus root 3 is equal to minus 3 is equal to constant by coefficient of x square. Verify that 3, minus 1, minus 1 by 3 are the zeros of a cubic polynomial p of x is equal to 3x cube minus 5x square minus 11n minus 3, and then verify the relationship between the zeros and the coefficients. Solution. Comparing the given polynomial with ax cube plus bx square plus cx plus d, we get a is equal to 3, b is equal to minus 5, c is equal to minus 11 and d is equal to minus 3. Further, we get p of 3 is equal to 0 and p of minus 1 is equal to 0. P into minus 1 by 3 is equal to 3 into minus 1 by 3 the whole cube minus 5 into minus 1 by 3 the whole square minus 11 into minus 1 by 3 the whole cube implies minus 1 by 9 minus 5 by 9 plus 11 into 3 by 3 into 3 minus 3 into 9 by 1 into 9 is equal to minus 1 minus 5 plus 33 minus 2 by 9 is equal to minus 33 plus 33 by 9 is equal to 0. Therefore, 3, minus 1 and minus 1 by 3 are the zeros of 3x cube minus 5x square minus 11x minus 3. So, we take alpha is equal to 3, beta is equal to minus 1 and gamma is equal to minus 1 by 3. We get alpha plus beta plus gamma is equal to minus b by a. Alpha beta plus beta gamma plus gamma alpha is equal to c by a, and alpha beta gamma is equal to minus d by a.
Division algorithm for polynomial. We know that a cubic polynomial has at most 3 zeros. However, if we are given only one zero, can we find the other two? For this, let us consider the cubic polynomial x cubed minus 3x squared minus x plus 3. If we consider that one of its zeros is 1, then we know that x minus 1 is a factor of x cubed minus 3x squared minus x plus 3. So, we can divide x cubed minus 3x squared minus x plus 3 by x minus 1 to get an equation x squared minus 2x minus 3. So, all the three zeros of the cubic polynomial are now known to you as 1, minus 1 and 3. As in positive integers, for polynomials also, we have f of x is equal to g of x into q of x plus r of x. We find that either r of x is equal to 0 or degree of r of x lesser than degree of g of x. Here, the polynomial f of x is called dividend. Here, the polynomial g of x is called the divisor. Here, the polynomial r of x is called remainder.
On dividing 3x cube plus 4x square plus 5x minus 13 by a polynomial g of x, the quotient and the remainder were 3x plus 10 and 16x minus 43 respectively. Find the polynomial g of x. Solution: f of x is equal to 3x cube plus 4x square plus 5x minus 13. Q of x is equal to 3x plus 10. R of x is equal to 16x minus 43. F of x is equal to g of x into q of x plus r of x. G of x into q of x is equal to f of x minus r of x. G of x into 3x plus 10 is equal to 3x cube plus 4x square plus 5x minus 13 minus into 16x minus 43. G of x into 3x plus 10 is equal to 3x cube plus 4x square plus 5x minus 13 into minus 16x plus 43. G of x into 3x plus 10 is equal to 3x cube plus 4x square minus 11x plus 30. G of x is equal to 3x cube plus 4x square minus 11x plus 30 by 3x plus 10. We have g of x into 3x plus 10 is equal to x square minus 2x plus 3 into 3x plus 10.
Divide 3x square minus x cube minus 3x plus 5 by x minus 1 minus x square and verify the division algorithm. Find all the zeros of polynomial x power 4 plus x cube minus 9x square minus 3x plus 18. If it's given that two zeros are minus root 3 and root 3. Solution: given polynomial f of x is equal to x power 4 plus x cube minus 9x square minus 3x plus 18 has two of its zeros minus root 3 and root 3. X plus root 3 into x minus root 3 is equal to x square minus root 3 the whole square is equal to x square minus 3. Now we apply the division algorithm to given polynomial with x square minus